Welcome to this puzzle session. Here is the problem. Suppose X is an n element set, meaning it is a set of size n is some positive integer. And we have selected more than half of all the subsets of X. So collect or form all the subsets of X and then choose more than half of them. We want to show that some two distinct elements selected have the property that one is contained in the other. Okay. So as soon as we select more than half of all the subsets of X, we are bound to choose two different things such that one is contained in the other. Here is an example. X is this three element set. Then all the subsets of X are written down here. And suppose we select more than half of them. Now, how many of them are here? 8 of them are here. More than half would mean at least 5. So suppose we select, let's say maybe this one, that one. Now, of course, if we select this, or that, then we already would have the property that one is contained in the other. But I mean, if you just try, whatever you try, you will see that you will be bound to choose two different such that one is contained in the other. So here this is contained in that or that. So just maybe experiment with it. It's an interesting puzzle. And our solution, yeah. So before we get to the solution, you're encouraged to pause the video and find your own solution. And with that, let us now continue. Okay. So we will prove this by mathematical induction or the well-ordering principle, if you like. For the purpose of this lecture, we will use some standard set theoretic terminology and notations. There is a whole playlist called Kickstart. The link is in the description below. So in this playlist, you can find all the basics of set theory, elementary set theory that we will be using. Okay. So we start with contradiction. Assume on the contrary that the proposition is false. Right, the proposition was that if you have an n element set and you select more than half of all the subsets of it, then some two different chosen subsets will have the property that one is contained in the other. We are assuming it is false, so there must be some n for which this does not hold. So by the well-ordering principle, if you like, we may settle on the smallest n. So let n be smallest such that there is a counterexample for that n, such that the proposition fails for that particular n. Right, so this is the smallest positive integer for which one can find an n element set and a selection of more than half of all the subsets of that set, with no two different having the property that one is contained in the other. Right. Why can we? We just used the well-ordering principle, but just to say as to why such a smallest thing should exist is the following. Once we assume that the proposition is false, we can collect all the n's which are bad, for which the proposition exhibits a counter, or for which one can exhibit a counterexample to the proposition. And amongst all the bad things, you can just select the smallest one. Okay. Fine. And just by experimentation, one can see that n must then be greater than or equal to 3. Why? Because for n equals 1 and n equals 2, one can just experiment. One can write down all the possible examples and see that yes, indeed, the proposition holds for n equals 1 and n equals 2. So we just assume that n is at least 3. And this is just for convenience. Okay, so now without loss of generality, we can say that our set, for which one can select more than half of all the subsets with define the proposition, we may assume that x looks like this, doesn't really matter, and f, so this is read as script f, but I might keep calling it f. Okay, so script f is a subset of the power set of x, which is a notation for all the subsets of x, rather the set of all subsets of x. This is called the power set of x. Okay, so we have chosen f as, or script f as a subset of the set of all subsets, meaning f is a collection of subsets of x, a collection such that f has more than half of all subsets of x, and with the property that there do not exist two distinct members in f one of which is contained in the other. So in short, all we have said so far is that, well, this was the smallest positive integer for which there was a counterexample. We have just fixed a counterexample, that's all. That counterexample is f. Okay. So now define two things. One is fn. So this is all those things in f which contain n, and this is all those things in f which do not contain n. Okay? So in words, it is just those things in script f which contain n. This is those things in script f which do not contain n. And clearly, one can see that script f is partitioned by these two things. Either a member of script f will contain n or it will not. So f is the disjoint union of these two things. So this symbol just means disjoint union. It is expressing that these two do not intersect and that their union is this. That's just a nice notation. Okay. Also, note that thus either this or this will happen. It just follows from the orange thing. If two things partition your something, then the size of one of them should be at least half of the size of the whole thing. Both can happen simultaneously when the sizes will be exactly half, but at least one of these things must happen. Okay. So now we will make two cases. Case 1 is when fn prime has size at least half. Okay, so in this case, note that fn prime is after all consisting of subsets of x which do not contain n. So it is in particular a subset of this set, meaning each of its elements is a subset of this. That's what this says. So this is clearly true. And since we have assumed, in this case, we have assumed this, we have that the size of fn prime is at least half of the size of f, but the size of f is at least half of the size of power set of x. That was the hypothesis on f, which is half of. What is the size of power set of x? It is 2 to the power the size of x, right? So this is a standard thing, that if x is an n element set, then the size of the power set of x is 2 to the power n. This is something we learn in high school also. So this is 2 to the power n plus 1. In fact, this is an equality. So this gives us, this is equal to, which is equal to 2 to the n minus 2 plus half, right? So in fact, let us just write it as half of. It's better to write it as half of that thing, which is equal to half of the size of power set of 1 up to n minus 1 plus half, which is strictly greater than half of power set of 1 up to n minus 1, right? Now, n was chosen as the smallest positive integer for which there was a counterexample to the proposition, and therefore n minus 1 had the property that there is no counterexample to the proposition, meaning whenever you select a subset of power set of the first n minus 1 natural numbers with the property that it has at least, or rather exactly, it has more than half of all the subsets, then you can find two distinct things here which have the property that one is contained in the other. So therefore, by the minimality of n, we can find two distinct members a and b in Fn prime such that one is contained in the other. And any two members of Fn prime are, after all, members of F. So once we have found two distinct members in Fn prime with this property, the same two elements also exhibit containment in the larger set script F, and that's a contradiction because we had assumed that F was a counterexample. So this is a contradiction. So case 1 leads to a contradiction. Now we will deal with case 2. Case 2 is slightly more interesting. Case 2 is that this is at least half of script F. Okay, so here we will slightly edit the set Fn. So define this set as you take away little n from each member of Fn. So this notation, it's not working for some reason. So this notation that we have here, it just means, well, first of all, A already has this, the set A already has the element n in it. We are just creating a set. This orange thing is supposed to highlight the set which has everything that's there in A except for the element n. So we are just taking out the element n from A. Okay, and for some reason my laser pointer is not working. Yeah, now it's working. So this is just all the elements of A except for the element n. Alright, so note that this is same as that. It's a very simple observation. Each member of Fn already had the element little n. We are just editing every element of Fn. So then, in particular, this is a subset of power set of that. And by our previous reasoning, one can find two distinct subsets. Let's call them maybe S and T in Gn, which are distinct, and S is contained in T. Right, and now S union little n is contained in T union little n, but S union little n, if you let us call it something, let's call it A, and this let's call it B, then A and B are members of Fn, and of course they will be distinct because S and T are distinct, and A is contained in B. So now we are done, because now we have found two distinct elements in Fn with the property that one is contained in the other, and hence two distinct elements in F with the property that one is contained in the other. So that finishes, this again gives a contradiction, and so what we see that in any case we have a contradiction, and hence our assumption that the proposition is false must be false, and we are done. So this finishes the proof. I hope that you were able to enjoy it, and as usual, like, comment, share, subscribe, and I will see you next time.